Section: Introduction. In this section, we discuss the widespread use of large language models, LLMs, in various real-world applications that involve processing long sequences of information, such as answering questions based on lengthy documents and creating summaries. These applications often require LLMs with a long working context, also known as long-LLMs, to handle the complexity of the tasks. However, developing and deploying long-LLMs pose significant challenges. Many existing LLMs are initially designed with a limited context size, like 2K for Llama 1, 4K for Llama 2, and 8K for LLAMA 3. While it is possible to fine-tune these short LLMs to work with longer contexts, it comes with high costs and resource-intensive deployment processes. Continuous training to extend the context may also affect the overall performance of LLMs on shorter contexts. Finding efficient and effective solutions to address tasks requiring long contexts remains an open problem. We propose that most tasks needing long contexts can actually be solved by strategically working with shorter contexts. For example, tasks like reading comprehension or summarization of a book can be accomplished by extracting key information from the text. This approach mirrors how humans and computers tackle complex problems by breaking them down into manageable parts despite limited memory capacity. However, solving long context tasks solely based on short contexts is not straightforward. Different tasks demand unique ways of accessing and utilizing information from the long context, making it challenging to have fixed rules for all situations. To tackle this challenge, we introduce a method called LC-Boost, which leverages short LLMs to address general long context tasks in a step-by-step manner. LC-Boost involves two critical reasoning steps: access, where the LLM plans how to access relevant context, and utilize, where it determines how to effectively use the accessed information. This adaptive approach allows LC-Boost to handle diverse long context tasks based on their specific requirements. We conduct experiments to evaluate LC-Boost on various real-world long context problems like question answering and document summarization, as well as synthetic tasks. Our results show that LC-Boost performs comparably to strong long LLMs like GPT-4 128K and even outperforms them in some cases by eliminating irrelevant context. Additionally, LC-Boost surpasses short LLM surrogates with predefined context access and utilization strategies, highlighting the importance of reasoning and adaptability in solving long context tasks efficiently. Section Summary. In this section, we introduce the challenges associated with learning and deploying long large language models, LLMs, for tasks requiring extensive context, such as long document question answering and summarization. We propose a method called LC-Boost that leverages short LLMs to effectively solve general long context tasks by strategically accessing and utilizing information from the input. Through comprehensive experiments, we demonstrate that LC-Boost can achieve performances comparable to strong long LLMs like GPT-4 128K, highlighting the importance of reasoning and adaptability in addressing long context problems efficiently. Section: LC-Boost. In this section, we define LLMs as models that take a user query Q and produce an answer, Y, using a selected LLM represented by gamma, CDOT. However, LLMs often struggle with outdated or in-depth knowledge due to their static parameters. To overcome this limitation, we introduce external knowledge, referred to as context X, into LLMs. Tasks like summarization also require a context X, along with the user query Q. The model's generation process with respect to a context X can be generally defined as Y equals gamma Q X. In many cases, the context X is a long sequence, posing a challenge for LLMs designed with limited context sizes, e.g., 4K. This leads to the long context problem, where LLMs struggle to process inputs exceeding their context limit L. One way to tackle this issue is by increasing the ILM's context length L. However, in this paper, we explore solving long context tasks using short context LLMs, e.g., 4K, without extending the model's context length L. Despite the potential to fine-tune LLMs for longer contexts, it comes with high costs. Processing long contexts during inference significantly increases computing resource consumption. To investigate if most long context tasks can be solved with short contexts, we conduct a pilot study from theoretical and empirical perspectives. In our theoretical analysis, we aim to find a subset (X), subset X, that captures relevant features of the input variable X. Concerning the output, Y, we propose a Markov chain X, right arrow X, right arrow Y, where X serves as a simplified representation of X, preserving the mutual information I, X, Y. By decomposing X into subsets and using a compression function, we can estimate an optimal X from shorter contexts X_1, L dots X_n. This approach helps in processing each subset individually, reducing computational complexity. Section Summary. In this section, we define LLMs as models that produce answers based on user queries and embedded knowledge. To enhance LLM's ability to handle long contexts, we introduce external knowledge and explore solving long context tasks using short context LLMs without increasing the model's context length. Through theoretical analysis, we propose decomposing the input variable into subsets to estimate an optimal context that preserves relevant information for generating the output, thus addressing the challenge of processing long contexts efficiently. Section: Empirical Analysis. In this section, we conducted experiments to evaluate how well we can estimate the minimal necessary context X by using decomposed short contexts X_1, L dots X_n. We performed these experiments using GPT-4 for tasks that require long contexts. We compared two settings. One where we input the entire long context directly into GPT-4 to generate the output answer, and another where we decomposed the full context into short contexts to approximate X before instructing the model to produce the final output, the LC Boost setting. The results showed that generally, LC Boost performed as well as or better than the brute force setting, especially excelling in tasks like QA, few-shot learning, and synthetic tasks. This success is attributed to the ability of LC Boost to filter out irrelevant context from X by identifying supported context from the decomposed short contexts. For tasks such as summarization and code completion, where considering mutual dependencies among all decomposed short contexts is crucial, the LC Boost setting faces more challenges. However, with an optimal compression function like GPT-4, we can achieve the best estimation of X, leading to performance equal to or slightly better than the brute force setting in these tasks. Our empirical analysis suggests that estimating X from decomposed short contexts is often more accurate than from the long context X, indicating the advantage of using short contexts over the full context in most cases. We introduce LC Boost as a method that leverages short LLMs to solve long context tasks effectively. LC Boost aims to extract the minimal necessary context X from decomposed short contexts X_1, C dots X_n to generate the output answer Y. Through a decision-making process involving interactions with the short contexts, LC Boost accesses and utilizes information strategically to achieve this goal. The actions taken by LC Boost include analyzing the query, retrieving text evidence, moving to the next short context, generating relevant context independently, merging relevant context with previous information, answering the query, and aggregating all relevant information. Although LC Boost's action space consists of only 7 actions, it proves to be a versatile framework for solving various long context tasks. Its effectiveness lies in its flexible accessibility to short contexts, accurate information acquisition, and dynamic answering capabilities. Our pilot study showed that even when paired with GPT 3.5 instead of GPT-4, LC Boost still demonstrates significant effectiveness. Therefore, we chose to use GPT 3.5 as the foundation model for LC Boost in our subsequent experiments. Section Summary. In this section, we empirically evaluate the accuracy of estimating the minimal necessary context (x) using decomposed short contexts x_1 L.x_n. Our pilot experiments using GPT-4 128K show that the LC Boost method, which decomposes the full context into short contexts, performs as well as or better than the brute force setting for tasks like QA and few-shot learning. LC Boost strategically extracts the minimal necessary context from short contexts to guide the model in producing the final output, demonstrating that most long context tasks are solvable using short contexts. Section: Experiment Settings. In this section, we assess LC Boost and baseline models on various datasets, including single-doc-QA, multi-doc-QA, summarization, few-shot learning, synthetic task, and code completion. We compare LC Boost with short-LLMs, long-LLMs, and closed-source LLMs. During the experiments, if the context length exceeds the model's limit, we trim the context from the middle to ensure crucial information is retained. The main results show that LC Boost outperforms baseline models in most tasks, except for the code completion task. Long LLMs generally perform better than short LLMs, but their performance varies across tasks. LC Boost consistently outperforms GPT 3.5 Turbo 16K across all tasks. To study the importance of LC Boost's design, we conduct ablation studies by altering LC Boost's action space, resulting in different information acquisition strategies. These strategies show that LC Boost's dynamic capabilities lead to significant performance improvements, especially in QA tasks. In the few-shot learning task, LC Boost's performance is not significantly better than fixed strategies due to the task's inherent guidance from in-context examples. In a case study on the self-constructed dataset, we demonstrate how LC Boost effectively solves challenging cases by customizing solutions for each query, leading to accurate results with shorter context lengths. LC Boost's dynamic approach simplifies tasks by processing only relevant information, akin to human reading comprehension. Additionally, LC Boost addresses issues with conditional reasoning and entity differentiation that traditional LLMs struggle with. Section Summary. In this section, we evaluate LC Boost and baseline models on various datasets spanning different tasks such as single-doc QA, multi-doc QA, summarization, few-shot learning, synthetic tasks, and code completion. Our LC Boost model, with a context length of 4K, outperforms baseline models in most tasks, showcasing its effectiveness in handling long context tasks by strategically processing decomposed short contexts. Through ablation studies, we find that LC Boost's dynamic information acquisition strategies significantly improve performance, particularly excelling in tasks like single-doc QA and multi-doc QA by accurately selecting relevant context and filtering out irrelevant information. Section: Context be short, energy be saved. In this section, we have observed the impressive rise of large language models, LLMs, in our daily lives. We anticipate that LLMs will soon be as common as electricity or gas, playing a crucial role in society. As LLMs become more prevalent, their energy consumption will become a significant environmental issue. Therefore, it is crucial for us as a research community to focus on reducing the energy usage of these models. We analyzed the energy consumption of LLMs by comparing the brute force method with our LC Boost approach. The energy consumption was measured in joules on the y-axis for 7 billion LLMs with different context lengths. We estimated the energy consumption theoretically using a formula based on floating point operations and GPU power. The practical energy consumption was determined by recording GPU time and power during inference with varying context lengths. Our analysis showed that longer context lengths significantly increase energy consumption with the brute force method, especially in practical scenarios. This increase is mainly due to the need to distribute sequence activation tensors across multiple GPUs, leading to higher energy costs. In contrast, our LC boost method, operating with 4K context lengths, demonstrated only a slight rise in energy consumption across contexts, highlighting its energy efficiency while maintaining high performance for long context tasks. We also conducted an analysis on token consumption, which is detailed in the appendix. Dealing with long contexts is a key challenge for LLMs, as many real-world applications require processing of extensive inputs. Researchers have explored different approaches to tackle long context tasks, such as increasing the working context size of LLMs. Some recent models have extended their context lengths to over 100K, showcasing the trend towards larger context sizes. Another approach to handling long context tasks involves extracting a shorter surrogate context from the full context. Techniques like retrieval, augmented generation, and context refinement methods have been proposed for this purpose. These methods aim to manage long contexts effectively, ensuring semantic coherence and preserving information integrity. Reasoning-based methods have also shown promise in addressing long context tasks by employing decision-making processes and reasoning techniques to navigate through extensive contexts. In our work, LC Boost incorporates a dynamic decision-making process to customize the action trajectory for each query, offering flexibility in accessing and utilizing information to generate accurate output answers.